Hi everyone, this is probably the most in-depth video you'll ever see on how to cut the aerodynamic drag of a car. We ran almost 300 simulations together with Zweig, a German manufacturer of three-wheelers. And we're going to divide this video into 4 distinct phases. First of all, the hangover. We woke up, we looked into the mirror and we saw that the existing design was actually really bad in terms of aerodynamics and we were not going to get the range that we wanted. Phase 2, applying makeup, trying to tune and squeeze the existing design to get some drag reduction out of it, but we concluded it's not going to be worth it, we need to go more drastic. So phase 3 is a complete facelift. Take this off, put a new one on, and then start to make proper progress. And then the 4th phase is really nice. We're going to talk about not just the external looks, but also about the inner side of ourselves, and realize that we also need to look at the flow distribution inside to have a good ventilation system. Now, before we dive in, why are aerodynamics so important? Well, if you are driving at highway speeds, around 70–80% of the energy you're using, whether it's a combustion engine or your electric drivetrain, is to just push air out of the way. So if you can cut the drag by 30%, you can actually extend your range by about 20%. Isn't that massive? It definitely is. So let's dive in. So this is phase 1, which is the hangover. We went to a party, we thought our design was actually already good and sound, and then we looked into the mirror, ran an analysis on AirShaper and concluded, oh, this is actually not as good as we had planned. This has a drag coefficient of 0.311. We thought, well, this is a wedge shape, it should actually slice through the air quite nicely. It has only 3 instead of 4 wheels. What can go wrong, right? But in terms of aerodynamics, a lot of these things are in the details, and something that can look aerodynamic, like an old Volkswagen Beetle that we tested on this channel as well, can actually be very unaerodynamic due to small changes, due to things sticking out and so on. So let's dive into the details of this phase 1 and analyze why this is actually not as aerodynamic as it looks. So at the front, we have the front wheel here, and we can see the front splitter. So the front splitter is actually quite sharp here, so the air hitting the front and then needing to dive underneath here, this one creates flow separation. Not a massive problem, but this can definitely be optimized. Then we have what we started calling, or what Zweig started calling, the potato shape. So as you can imagine, if you have just one front wheel and it needs to rotate to steer, you need actually this cutout here to allow it for space to maneuver around. So this is to be left open, but if this is left open, that means that the flow can actually enter this area here, create a lot of fuss inside this space here, and then come out again with a lot of turbulence. And you can see that this turbulent wake here of the front wheel and the potato shape spills down all the way to the rear of the car and even pollutes what is happening in the diffuser of the car and triggers flow separation there as well. So it's not just the wheel causing drag, it's actually the effect on the rest of the airflow on the car as well. So this is a massive focus area. There was already an air deflector to guide the air around the tire to avoid big spillovers, but that was not enough. We also saw that there is a lot of geometry sticking out at the bottom of the car, so you really need a flat, smooth underfloor if you want to maintain that momentum all the way to the end of the car to feed the diffuser and to reduce the size of your wake and maybe get some downforce in the process. What we also saw then is that at the headlights, if these are left open, that means the air will hit them full on and then splash out, jump across, jump to the side, speeding up, which creates this low pressure area. And as you can see, creates this wake around the front headlights. Then the air making it past the headlights would actually jump across this small ridge here and then jump across the windscreen wiper, but it wasn't entirely jumping across. Some of it was still hitting the windscreen wiper, so flow separation in this area as well. Then the flow would curve around the front A-pillar, and even though it's fairly nicely rounded, it was actually still too sharp, and in combination with some small disturbances you would get flow separation, and of course your A-pillar vortex starts to curl up over here and eventually reaches the roofline. Then we saw that this B pillar, which is kind of sticking out, was also disturbing the flow, and the interaction with the mirror was also not really beneficial to the flow. You can see that the A pillar vortex and the mirror are actually joining forces in a quest to reduce or to increase your drag coefficient. Then we see all of this dirty fuss here at the top of the car. And yes, we did run simulations at higher accuracy, but the bulk was done at medium accuracy. But even at medium accuracy, you would spot that these gaps that you have between the windscreen and the bodywork and other panel gaps like here. So these are actually kind of like gullwing doors. If I'm not mistaken, they trip the flow, and this actually creates a dirty layer of air on top of the car, which travels all the way downstream. Then there's the added problem of the hinges. So if you want to open up the trunk here, these are the hinges. And then we have the B-pillar, which again, because of the panel gaps, things sticking out, creates flow separation. Then we had a very interesting, challenging area here. So at the hips of the car, they curve down nicely. It's a very short overhang, which is nice if you want to park your car in a very tight spot. But in terms of aerodynamics, this sharp downward curve here makes the air want to stick to it, and this accelerates. So just like on the original Audi TT, which had a nice butt, but then again, the air would want to stick to it, and this this low pressure air, because it speeds up, separates at some point, and this low pressure area that you start to see here on the hips actually creates a kind of a suction effect, pulling the car backwards. So that is a key area that we improved as well. Of course, the wheels have their own wake, so the air hits the wheels and then creates a wake around it. We can see that there's flow separation inside the diffuser. So at some point across the entire width, the diffuser features separated airflow. So, and then we have the roof line. So we did have a spoiler already to guide the air downward and into the wake to reduce the size of the wake. But again, if you have the wrong curvature here at the top of your car, this will actually create a suction effect, create lift on the car and create drag on the car, which is not what we wanted. So just an overview, this is the pressure map, this is the friction map where you can spot areas of flow separation. The wheels themselves, of course, the rear of the car, fully separated airflow, which is normal. You can see the effect of the hinges traveling downstream, this turbulent air, separated airflow. This is the dramatic effect of the front potato, the central wheel. So all the way down to the diffuser, separated airflow, and then this separation spreads out left and right as the flow cannot maintain momentum and attachment to this surface. So massive challenges ahead. So that means for the second phase, we were going to apply makeup to this design. The scope was clear. This is our design. Let's now tweak it. And the goal was a drag coefficient of 0.22, coming down from 0.31, which is a massive challenge. And we were going to do this with this design. So bear with me as I walk you through the efforts that we did. So if we want to look at this, we actually ran a design advice simulation first. Now this is kind of a special simulation which still uses mathematical equations. It's not based on AI, it doesn't need to be trained or anything. It just directly uses an extra set of equations to point you into the right direction. So what you see here in blue and red is a color map indicating where you should move the surface inward and where you should move it outward, which is red. So blue is inward, red is outward along the surface normal to reduce the drag. So as we saw, if you want to reduce the drag on the headlights, you actually want to reduce this sharp edge at the front, push it down, which is the sharp edge here that the air needs to cross. And then you want to have this bulge here to provide a soft landing zone for the air. So push this edge down, push this up, so to give a more rounded shape. You have a sharp edge here, so again the software is telling us blue here means push it down, and the ramp behind it push it upward, so you have a softer transition. And so this really provided us with massive clues as to where we could improve the aerodynamics. Also the front wheel deflector was showing up a lot of room for improvement, so it wanted us to push this in, push this down to increase the deflector effect, close this gap here, so make this more continuous, which is what the red is telling us. Around the mirrors, a lot of room for improvement to just push downwards this surface here to make the flow work better with the A-pillar vortex. This area is red to just indicate we should shoot the air a bit more across the tire to avoid mixing effects there. The spoiler was telling us to put this downward and then give it a small kick at the rear to recover some of the pressure. A different area on the sides here because the central flow is different from the side flow. At the hips, a lot of suggestions here on how to tackle that flow. The diffuser, as we mentioned, the air deflectors which are there. So lots of room for improvements. To do this, we went, or actually together with Twike, we went through a massive number of simulations. This Excel is just a very small overview of what was done to run improvements. So what you see here is an overview of the automated morphing simulations that we ran on the car. This is the first. So we allow the software to automatically optimize the shape of the car. So what we asked here is please work on the front of the car, and here you can see that extended the nose to be a bit sharper, to pierce through the air and to reduce the pressure buildup around the car. This gave us a marginal improvement, but it's something. Then we did the same for what we call the front air deflector, which is a small bit that helps to shield the front tire. So this part here, if you look at the optimization, we can again see that there are some minor improvements. So if you push this outward more forward and keep this small ramp here, you push the air more downward and away from the tire, and you get again some marginal improvements in the drag. If we then look at the diffuser, another critical area, it's a bit harder to see on this one, but this clearly showed massive potential for improvement. So if I slide this one back and forth, you can see that the diffuser is being pulled upward in the midsection and then keeps the same height at the end. So instead of a straight or an angled curvature for the diffuser, we were now getting an S shape, which is nice because you pull the air up to reduce the size of the wake, but then you flatten it out again to have some pressure recovery to avoid that suction effect that will drag your car backwards or cause drag on your car. Then what we did is to run a optimization on the roof, also a very critical area. If you look at the Toyota Prius, for example, or a Tesla Model 3, you can see that they have kind of a cab forward design and then a long, slender slope for the rear roof. In this case, we're kind of stuck to this backward cabin design, cab backward design, where the nose is longer than the rear of the car. So that is what we had to work with, because the windscreen was a thing we could not touch. These parts were already carved in stone, so we had to deal with whatever we could starting from this hinge line. So we ran an optimization, and here you can see that the software told us to lower the spoiler but then still provide a little kick to the spoiler. It hinted us at a certain potential for drag reduction, definitely sizable, 0.007 in terms of drag reduction. And then what we did is to run an optimization on the front splitter, so left and right of the nose. We wanted to see what would happen if we would change the geometry left and right of the nose. So, and this is what happened. So very interestingly, the software was pulling up the splitter dramatically, and this is counterintuitive. Most people want to keep the splitter low and sticking it out forward to prevent air from getting underneath the car. But if you can get more air underneath the car, you can provide more momentum, which really helped in our case to close the wake behind that front wheel that we had. So if you remember, this is the wake that we had, and this is like slow air being dragged along. So if you could feed high-speed air into that wake, that would really be beneficial, and that is what this suggestion was actually telling us. Now, the thing is that all of these things combined, we went from 0.311 to 0.28, which is still not what we wanted. After all of these changes, all of these small modifications that we did, that is still what we were left with. So then what we did for phase 3, because we wanted to go from 0.28 to 0.22, which is still a massive challenge, the customer Twike actually concluded, normally it's us telling them, but they told us we need to be way more drastic. We need to get the drag down, and we need to question everything we did so far. So we went for a massive brainstorm session together with the guys at Voyager, friends from way back who run a design agency here in Belgium, and we got to work. So this was the clear brief. We want to go from 2.8 to 2.2 in terms of drag coefficient, 0.28, 0.22. Which are the areas which are fixed, which we cannot touch because they've been carved in stone, because they already have molds and so on, and which are the areas that we can still modify. What can we do to actually bring down the drag coefficients? So then we started brainstorming. So digital brainstorm on a physical whiteboard and so on, placing virtual post-its on different areas. Can we reduce the frontal surface area? Can we change the shape of the cockpit? Can we extend the flanks aerodynamics. Can we change this part here? Can we do something like the Chiron to have an open rear to ventilate some of the wheel arches? Can we extend the length of the car like a long tail, which is what they do for speed record cars? Can we apply two massive tunnels at the front of the car to feed some high energy air or high speed air next to the front wheel to reduce that wake? Can we use internal channels to feed air through the bodywork of the car, and so on? These would be the channels and so on. So then we prioritize the things that we wanted to analyze. Can we put a small gurney flap to make the air jump across the front lights and then land at the right spot without creating drag? Can we integrate the mirrors into the A-pillars? Can we put seals on the panel gaps? Can we change the geometry of the spoiler, and so on? Loads and loads and loads of changes. And then we went to work to actually start to prioritize this, combine this with constraints like, of course, the mechanical structure. I mean, the design is one thing, but you still need to fit people and a car inside. We already had a mechanical structure for the suspension. The hard points were clear, so we couldn't actually move the bodywork in there. So we tried to work our way around these hard points, come up with different concepts, draw inspiration from existing cars. Obviously, this is what you do when you design a new car. This is the Lightyear one, an Audi concept a long time back, and so on. So we started playing around and we came up with numerous and numerous developments. So some of the examples here, we looked at fans, we looked at diffuser geometries, like the almost straight diffuser. Is that the best solution? Should we go for more like an S shape, like what you see on the Gordon Murray, even though that one has fans? Can we change the nose of the car? Can we do something about the length? All of these things were questioned and actually executed. And here you have just a small overview out of the 280 simulations. You see all of the things that we did. You can see we went actually back to the basics. So at some point we said, well, let's just go to a very basic shape because we don't know with all of the details which part is having which effect. So the first thing that we did for phase 2 is what they call the soap model. And this is a soap model because if you have a piece of soap and you use it quite often, it becomes nicely rounded. And we wanted to start with a very clean shape, only to have a closed shape here at the wheel. So we don't even have the potato shape, but we did have the basics in there, the drag around the wheels and so on, just to see what is theoretically possible if you take away all of the detail. And of course, we wanted to go beyond this because this had a drag coefficient of 0.262, which is down from 2.8 on the detailed car design. But now we had to start modifying this one as well. So one of the first things that we did is to work front to back on this car. And we ran an optimization on the nose of the car to actually find out what if you would add channels here, like we saw in the optimization, if you would provide clean airflow underneath the car instead of pushing it away left and right, like we saw on this one. So this one pushes air left and right. This one actually has a very rounded shape to promote air to go underneath the car and to fill the wake behind the wheel. And the effect is massive. Just have a look at, even on this simple soap model, we were able to maintain a very closed shape, and what is more interesting, you can see that we have a nice energetic flow going towards the rear of the car. So doing this brought the drag down already to 248. Now then the thing was we had to put back the potato shape. So putting back the potato shape increased the drag again to 266. So it felt like we were back to square one, but that wasn't the case. Because then we started modifying the potato shape by adding nice rounds actually to this cutout, so that the air which would actually dive into the potato shape would actually land on a soft spot. So here we're going to look at the dramatic effect of the potato shape, which means if you put it back, you can see that the wake increases again and this area becomes filled with dirty air. So what is happening is that the air would get trapped in this cavity, then had to exit again across this edge, and that would create turbulent airflow and again give you that draft or that drag zone that extends all the way to the diffuser. Not as dramatic as before, but there was room for improvement. So optimizing this shape with nicely rounded edges here on the potato brought the drag back down to 0.24. 0.48, for example, in this case. Then we also worked on further optimizations of the diffuser, but then this time applied to this clean shape. So if you look at the optimization here, we saw that there was a lot of room for improvement to go from 0.236 to 0.232. Slightly higher, and again the software was telling us to bring back this dent in this diffuser, which is this S shape that we saw. Then we started doing the exact same thing on the roof of the car, and here you can see the final result of all of these modifications combined. I'm just showing you the tip of the iceberg. We looked at the mirrors, we looked at the A-pillar, we looked at the hinges on top of the car, and we were left with a drag of around 0.22, slightly higher, but we're still going to push it further down on this car. So really dramatic improvement. We have these nice channels side by side here, funneling air underneath the car. The windscreen wipers are nicely shielded. Panel gaps have been reduced a lot. Mirrors have been optimized. We have optimized the diffuser massively. So what we did in the end, we played around with channels on top of the suspensions and so on. But in the end, the conclusion was the simple shape here with the suspension still tucked inside was the best one. So we have a shape here of the diffuser which goes up like this and then flattens out again, which is the S shape that we also see on top of the car. This really helped to reduce the drag dramatically. We also have sidewalls here which provide a shielding function in between the spillover air of the tire and the diffuser, so the spillover of the wheels stays close to the ground and doesn't pollute the attached airflow in the diffuser. We had to work our way around the option to have a trailer hitch on the car, which is a really interesting challenge. We had a hard point here because that's where the frame of the car was positioned. So super interesting project where we cut the drag by a dramatic amount. And now, after all this facelifting work, which is on the exterior, we're going to come to the really nice truth. It's all about what's inside, right? So let's have a look at the internal flow, because now we want to optimize what happens if you push air into the cabin. How does it actually distribute along the cabin volume, along the passengers and so on. So let's have a look at that one as well as a bonus. So here you can see an analysis of the ducting system. And what we're doing is we're applying inlet air here at a certain flow rate, and then that flow will distribute among the different outlet channels. So over here, these are the outlets that will actually defog or demist the window on a cold day. So you have to imagine that this is the car, and this ventilation system is somewhere over here, and these slots of air are actually right underneath the front window. And that's what we're looking at here. So the front window is actually over here, and this is where the air comes out. We also have these ventilation holes, which are just left and right of the front passengers, and then these ones, they go down towards their feet, that area. And so what we can do with just one simulation is to analyze the flow distribution. This is already iteration 4 or 5, where we can compare the flow rate on this channel, which is a flow rate of 5.7 liters per second, and this one is 4.9, which is already way better than the initial concept, where we had deltas of 20, 30, 40, 50% between those different openings. And here we can also analyze how much flow rate we have on one channel, and as we move along the length of this channel, we can see that this varies, and we have different flow rates. So we're still in the process of further tuning this to make this as equally distributed as possible, to give you the fastest possible time to actually defrost your window or defog it. And then we want to have the same amount of comfort for passenger and driver. We want to keep your feet cool or warm depending on what you want, and so on. So that's it in a nutshell, the massive amount of work that we did, and we went all the way from a drag coefficient of 0.311 to 0.22, which is a 30% reduction, which means 20% more range. So if you're going on a city trip, that means you can just drive to the next biggest city on the same battery charge. How incredible is that? So if you were fascinated by this process, it goes way deeper than what we showed in this video. So reach out to us if you want to discuss your project. Hit the subscribe button and leave a comment if you want to start a discussion. So thanks a lot for watching. Have a fantastic day and talk to you soon. Bye bye.